Welcome back. Now that you've had an introduction to working with capacitors, we'll continue to look at how to incorporate them into projects, as well as look at a few other concepts that will be helpful when you work through the activities for this lesson. In this video, we'll look at capacitor charge time and working with them in parallel versus in series. We'll then move on to look at how to use a capacitive touch sensor, as well as male to female jumper wires. At the end of this video, we'll take a brief look at GPIO pin level sensing too. Now remember from the last video, capacitors have the ability to charge and discharge very quickly. Charge time is the amount of time that it takes a capacitor to fully charge. This value will be affected by factors like the capacitance value and the voltage level being used to charge the capacitor. Assuming a charging voltage of 3.3 volts, a 2200 UF capacitor will take longer to charge than a smaller 220 UF capacitor. Now, although the larger capacitor will take longer to charge, once it's charged, it can put out much more energy than the smaller capacitor. A capacitor that is allowed to fully charge will reach very near the voltage it's being charged with. So a capacitor being charged by 3.3 volts will likely reach somewhere between 3.25 and 3.29 volts. The time required to fully charge a capacitor can be computed by using a value called the RC time constant. 1 RC time constant is the amount of time required for a capacitor to charge to 63%. And 5 RC time constants are generally considered to be the time required to fully charge. The RC time constant for a circuit can be computed by using this formula. Series resistor in ohms multiplied by capacitor in farads equals 1 RC time constant in seconds. Since a microfarad is 1 millionth of a farad, the UF value of your capacitor must be converted to its farad value by dividing by 1 million. So a 2200 UF capacitor is divided by 1 million, which gives us 0.0022 farads. If a 1000 ohm resistor is used with a 2200 UF capacitor, the amount of time of 1 RC can be calculated by 1000 ohms times 0.0022 farads equals 2.2 seconds. This means that it will take 2.2 seconds for a 2200 UF capacitor to charge to 63% of the supply voltage when in series with a 1000 ohm resistor. To compute the time required to fully charge the capacitor, the single RC value would be multiplied by 5, and that gives us 11 seconds. 2.2 seconds times 5 equals 11 seconds. So a 2200 UF capacitor with a series resistor of 1000 ohms will take 11 seconds to fully charge to the supply voltage. Any less time than this and the capacitor will not be fully charged. To calculate the full charge time, which is 5 RC, on a 220 UF capacitor with a 1000 ohm series resistor, that's 1000 ohms multiplied by 0.00022 farads equals 0.22 seconds. So that gets us to 63%, right? And then if we take 0.22 seconds and multiply that by 5, we get to 1.1 seconds for the 220 UF capacitor to fully charge. You can see from this calculation that a 220 UF will fully charge much faster than a 2200 UF. In fact, it's exactly 1/10 the time. As seen in the image here, at the 1 second mark, the 220 UF is almost fully charged, while the 2200 UF is still only charged to about 30% of its capacity. This means to utilize the full capacity of the larger 2200 UF capacitor, it must be given at least 11 seconds to fully charge. While it might be nice to give the 2200 UF capacitor a full 11 seconds to charge, as you can see from this graph, after about 6 seconds, it's been charged to 95% capacity. And 95% capacity will likely be more than enough for any projects you plan to work on using capacitors. The chart shows a capacitor's charge level at each time constant. Most of the charge is stored during the first couple of RC time constants. After that, each additional RC time constant adds less and less charge. So for this reason, in the activities for this lesson, you'll only allow the capacitor to charge for 6 seconds. The RC value for a 2200 UF capacitor paired with a 1000 ohm resistor is 2.2 seconds. Allowing the capacitor to charge for 6 seconds is just short of the 3 RC value of 6.6 seconds, but this will be more than enough for the purpose of the upcoming activities. So let's move on and talk about using capacitors in series versus in parallel. Capacitors are exactly the opposite of resistors when it comes to calculating the total value of components in series versus parallel. With resistors wired in series, their total values is all the individual values added together, right? We did this back in level A. So resistor 1 plus resistor 2 plus resistor 3, we add all the resistors together, we get the total resistor value. So if we have 3 1000 ohm resistors, we add those together and we get 3000 ohms. Capacitors must be wired in parallel to achieve this same effect. So wired in parallel, capacitor 1, capacitor 2, capacitor 3, all together equal the total capacitor total. So if there are 220 UF capacitors, 3 of them would be 660 UF. In activity number 2 for this lesson, you'll build a program that will measure the amount of time that 2 capacitors in parallel take to discharge. Since these capacitors will be connected in parallel, their 2 values are added together to determine the total capacitance. So a 220 UF plus a 2200 UF capacitors will equal 2420 UF. Then the 2200 UF capacitor will be removed from the circuit, and its removal from the total capacitance will result in a drastic change in the measured discharge time. Now let's move on and talk about capacitive touch sensors, particularly the one in your kit. This sensor measures the capacitance of 4 touch pads and will toggle 4 output lines high or low based on which pads are being touched. Output lines will be low until a pad is touched, at which point the corresponding output will go high. This model of sensor can run the 3.3 volt supply by your Raspberry Pi, and this means that the output lines from the capacitive touch sensor will not exceed 3.3 volts, making them safe to connect directly to the GPIO pins on your Pi. When 3.3 volts and ground are initially applied to the sensor, it will determine the baseline capacitance of the 4 input pads. When you touch a pad after this initialization process, your skin will change the capacitance that is measured at the pad, and the output line for that pad will be pushed high. The sensor uses the baseline measurement to determine when a pad is touched or not. If you happen to be touching a pad when the sensor was first turned on, your skin capacitance would change the baseline value, and now the sensor would no longer be able to determine if a pad had been touched. To avoid this problem, make sure that you are not touching the pads when the sensor is initially powered on. Now, there is not much to working with this sensor as an input for your programs. It handles the capacitive touch sensing internally, so you end up with 4 outputs that switch between high and low just like any other switch input. Okay, let's switch gears here and talk about jumper wires. Your Level A kit included male-to-male jumper wires with pins on each end for making connections between locations in the breadboard. Your Level B kit includes male-to-female jumper wires with a pin on one end and a socket on the other. These jumper wires can be used as extensions to add space between devices that would normally plug directly into the breadboard. The capacitive touch sensor, for example, has 3 pins coming out of the top of the circuit board. It would need to be turned over to be inserted into the circuit board, at which point you would no longer see the signal names or the touchpad numbers. The male-to-female jumper wires included in your kit make it possible to connect the capacitive touch sensor to the breadboard while still allowing you to read the markings on top of the circuit board. Anything that would be normally connected directly to the breadboard could be connected remotely using the male-to-female jumper wires, and this includes the RFID reader, the temperature sensor, the ultrasonic range sensor, or even something as small as an LED. Before we move on to the activities, let's have a brief discussion about GPIO level sensing, as this will come in handy during the activities for this lesson. As you've seen throughout various projects, GPIO inputs are usually high or low to trigger different events in a program. Sometimes there are voltages that are slowly transitioning from high to low, like a capacitor going from charged to discharged. Connecting this capacitor to a GPIO input through a current limiting resistor will allow you to watch how slowly this high to low process occurs. The input will start out as high since the capacitor is charged, and then as the capacitor slowly discharges, the GPIO pin will eventually register as low. In the Raspberry Pi, this happens right around 1.4 volts. Voltage levels above 1.4 will register as high, and anything below 1.4 volts will register as low. The sensing of this high to low point will be a key part of the program that you create in activity number 2 that will time the discharge of capacitors from charged down to 1.4 volts. Okay, before you move on to the next video, let's take a few moments and review the concepts we've discussed in the last 2 videos. In the last video, we talked about capacitors being able to quickly store and discharge energy into other components. There are different sizes of capacitors available. The 2200 UF capacitor in your kit can store 10 times the energy as the 220 UF capacitor in your kit. While smaller capacitors may not be polarized, larger ones, known as electrolytic, are polarized. So be sure to identify the negative of the capacitor by the gray band and place it in the circuit in the correct direction. Capacitors can charge and discharge very quickly, so to protect the power supply in the GPIO pin, it's really important to place a current limiting resistor in series. And in the activities for this lesson, you'll specifically use a 1000 ohm resistor to moderate the current down to 3.3 milliamps, which is well within the safety limits for the Raspberry Pi's GPIO pin. And then in this video, we looked at how to calculate the charge time for various sizes of capacitors. Remember, charging to 100% isn't necessary, and by charging the 2200 UF capacitor for 6 seconds, we can reach about 95% of its capacity, which is plenty. We then looked at how to calculate capacitors connected in series versus in parallel. Then we moved on and looked at how a capacitive touch sensor works, and you'll get a chance to work with one in the activities for this lesson. And finally, we looked briefly at how to use male to female jumper wires and GPIO level sensing. Okay, go ahead and move on to the activities for this lesson, where you'll get some hands-on practice working with capacitors and the capacitive touch sensor.